Okay, so our last section in this chapter is to look at other operations that involve sets, and sort of deepen our understanding of the mathematics behind sets and some of the things that we can do with it. So let's start by looking at some ways that sets can interact. The first interaction we're going to look at is called an intersection. So let me write that out. Intersection. So the intersection of sets A and B, and we write that as A, looks like an upside down U, B, it's the symbol for intersection of, is a set of all elements that are common to A and B. Okay, so A intersect B, and set builder notation would be any number such that the number happens to be an element of A and an element of B. Okay. Now we can illustrate this using a Venn diagram. So let's put some numbers in here and kind of visually see this and illustrate that 4,800 individuals have college degrees, 5,400 earn 40,000, 1,200 earn, and 1,200 have a college degree and make at least 40,000. Okay, so let me start with our universal set. This is the world of our problem, and we have, let's do C equals college degree, and let's do S equals at least 40,000. Okay, so we have a college degree bubble and we have a 40,000 bubble. Okay, so under the college degree, we know that there's 4,800 of them. I'm going to hold off on that for just a second because I want to start with this overlap, this little area right here. That's the part that have both. And I know that there are 1,200 in both. So if I know that there are 4,800 college degree holding students, and 1,200 of them make over 40, then this other piece, this piece that's not under the 40,000 bubble, how much is that? Well, that would be 4,800 minus 1,200, or 36. So there's 3,600 students here. And notice when I add 3,600 and 1,200, I still get the 4,800 that represents the college degrees. Likewise, I know there are 5,400 students who make more than 40,000. So if I subtract off the 1,200 that I already know about, I get 4,200, and so that's right there. So that means there's 4,200 students that don't have a college degree that are making at least 40,000. Okay, another set property is a union. So let me write that out. The union of two sets A and B are written with A. This time it sort of looks like a U. It's not really because we're not really got that tail at the end, but it's A union B. It's a symbol for that. And this is the set of all elements in A or B. So let me write this out. A union B is the set of all things that either it's in A itself or it's in B. Okay? And the key word here is or, makes it a union. All right, the complement of A relative to B, so let me write this out here. Complement of A relative to B, written as, looks like B minus A, is a set of all elements that are in B and not in A. So let me write that out. So B minus A is any number such that that number is an element of B and an element of not A. Okay. Now we don't kind of warn you on this. B minus A is not said as B minus A. It looks like it, so it's not. We don't. It's not what that means. We use that as a symbol for the word complement. Minus is typically an operation dealing with numbers, and the set difference is when we're talking about sets. So I guess it's okay to think it in your head, but when you describe it, it's described as a complement. And then when someone says, what does that look like? You go, well, it looks like B minus A, but it's really not B minus A. Okay, just forewarn you on that. Okay, so just like numbers have properties, sets have properties. I'm going to remind us of this, even though I don't necessarily want us to use this notation with commutative properties. But when we talk about commutative property of numbers, we're saying that if I take two numbers and I add them together, order doesn't really matter. Okay, so for example, when we talk about set operations with commutative properties, then we're saying that the intersection of A to B is the same as the intersection of B to A. That when you're looking at the overlap, it doesn't matter which set you start with when you start identifying what elements they have in common. Associative property, so again, going back to numbers, this is where you were adding three things together, and so you had to pick the order you added them. So if I'm adding 1 plus 2 plus 3, in this case I would say, hey, let's start with 2 and 3 and then throw 1 at the end. Or I can move the parentheses around and I can add 1 and 2 together and end up still with the 3, and I still end up with the same operation. So sets also have that similar idea. So this would be the intersection of B and C. So the elements in A that intersect with the elements of B and C is the same as the elements of A and B that intersect with C. Those have the same characteristics. The union also has the same characteristics. So the union of A with the union of B and C means I could also union A and B first, and then union C. So you can kind of see that there's some similar characteristics to the way the numbers behave versus sets. They're sort of they look similar, even though we're talking about two different concepts. So with sets, we're talking about groups of numbers, whereas the numbers themselves are looking at physical adding things together. All right, so now we're going to practice is we're going to take a Venn diagram and we're just going to look at how to write in the notation we've learned what we physically see in the image. Okay, so in this first one, let's just describe it to ourselves. Looks like we have a universal set with A and B, and I don't want the intersection of A and B, but I want the stuff that's not, I want the stuff in A that's not in B and the stuff in B that's not in A, but I want to merge those together. Okay, so give us a couple of different ways that we could write this. I could say, look at everything in A and B, so the union of A and B, and take out the intersection of A and B. Okay, so that's one way to communicate that. I could also say take everything in A and B, so the union of A and B, and then take out the complement of the intersection. I'm sorry, not take out, or the things that are in the complement of the intersection. Okay, and then one other way I could describe this picture is I could say look at the stuff in A, but take out the stuff that's in B, and union that with the stuff that's in B but not in A. And all of those are valid statements, not one's better than the other, all of them have merit to it. Let's take a look at this other one here. We've got sets A, B, and C, and I'm looking at the stuff that intersects any two of them. So a couple ways I could write this. I could say, look at the intersection of A and B and union that with the intersection of B and C. Is one way I could do that. Or I could say it's the stuff in B that is also in the A or C. So anything in B that also happens to be that overlaps with A and C. Sort of another way to write that. So again, there's multiple ways that we can communicate that. And then let's keep going with this. Kind of scroll that over so we can kind of see a little bit better, maybe right there. All right, so let's kind of think about how else can we write this. Here in this picture, I want the stuff that's just in A, but nothing else shows up. So I could say, let's see, let's start with A, and let's take out anything in B. And then let's also take out anything that happens to be in C. And so that would just leave us with the stuff in A. Or I'll give you one more way to write this. I could say start with A and then take out anything that happens to have B and C in common. So both of those illustrate the same picture. Okay, this next one, oh wow, we got a lot of overlap, a lot of things to consider. Okay, so I'm just going to give you one way to write this, even though there's a couple different ways. All right, let's see. Let's start off with anything that's in A or C. So A or C, but we'll initially take off B. Okay, we're not done yet, but let's think about what that gives us. So A or C, and then take off B, means I wouldn't have this piece right there. So I need to include that little tiny piece there. Okay, because if A or C means I'm looking at all of A, and I'm looking at all of C, so I'm looking at those two circles, and I've gone ahead and I've taken off anything that has B in it, so that means this piece is gone. So then I need to include that piece. So, I'm sorry, the overlap where A, B, and C all have in common. So the union of the intersection of A, B, and C. And so that right there is this little sliver. So if I put those together, then that should be enough to describe this picture.